Bismillah ar-Rahman ar-Rahim. Alpha is a real number strictly greater than 1. Capital P is the set of prime numbers. We have a product of matrices, a product over the primes of the 2 by 2 matrices, 1, p to the minus alpha, p to the minus alpha, and 1. Our goal is to obtain this product. The most important observation here is that the matrix is a symmetric matrix, so it is guaranteed to be diagonalizable. If we have a product of matrices, say A1, A2, A3, A4, and so forth, suppose that those matrices are all diagonalizable and they have the same eigenvector matrix Q. A1 is Q, lambda 1, Q inverse. A2 is Q, lambda 2, Q inverse. A3 is Q, lambda 3, Q inverse, and so on. When we do the multiplication, this product is identity, that product is identity. We end up with Q, Q inverse, and the product of the eigenvalue matrices. We can simplify the product using eigendecomposition. Because our matrix is a symmetric matrix, then the eigenvectors can be chosen to be orthonormal. If beta is in R, the matrix 1 beta, beta 1 can be written as Q lambda Q transpose. Q is the eigenvector matrix. It is an orthogonal matrix. Q Q transpose is equal to Q transpose Q is equal to identity of size 2 by 2. The inverse of Q is Q transpose. The eigendecomposition is Q, then a 2 by 2 diagonal matrix lambda, having the eigenvalues of this matrix on the main diagonal, then the inverse of Q, which is Q transpose. The characteristic equation is the matrix lambda 0, 0 lambda, minus this matrix. We have the 2 by 2 matrix, lambda minus 1, minus beta, lambda minus 1. The determinant is lambda minus 1 squared, minus beta squared, that's beta squared. If we equate to 0, we have lambda minus 1 squared is equal to beta squared. Lambda minus 1 is plus or minus beta. Lambda is 1 plus or minus beta. The eigenvalues of this matrix are 1 plus beta and 1 minus beta. To obtain the eigenvectors, let's use the eigenequation. So here is the matrix. Let's put the eigenvector in this form. The first component is set to 1, and the second component is Q. The matrix times the eigenvector is the eigenvalue times the eigenvector. If we use the first row here, we have 1 times 1 plus beta times Q. This is equal to the first component, which is 1 times this scalar, which is 1 plus or minus beta. 1 goes away with 1. Let's take beta to be a non-zero real number. In this case, we can divide both sides by beta to obtain that Q is plus 1 or minus 1. The eigenvector associated with the eigenvalue 1 plus beta is 1 and 1. The eigenvector associated with the eigenvalue 1 minus beta is 1 and minus 1. Each one of these vectors has an L2 norm of square root 2. If we want the eigenvectors to be normalized, that is to have a unity L2 norm, we can divide by the square root of 2. The matrix of eigenvectors is this 2 by 2 matrix. 1 over square root 2, 1, 1, 1, minus 1. It is an orthogonal matrix. Its transpose is equal to its inverse. In our case, beta is equal to the prime p to the minus alpha. So we can write down this matrix as the matrix of eigenvectors. The eigenvalues are 1 plus p to the minus alpha and 1 minus p to the minus alpha. As we have seen in this general case, if we write down the product, we have matrices whose product is identity. We end up with Q on the left, Q inverse on the right, and then the product of the diagonal matrices. This product is over the primes, 1 plus p to the minus alpha, and this product is the product over the primes of 1 minus p to the minus alpha. 1 plus p to the minus alpha times 1 minus p to the minus alpha is equal to 1 minus p to the minus 2 alpha. This term here can be written as 1 minus p to the minus 2 alpha over 1 minus p to the minus alpha. We can split this into two products. To finish off the problem, we need this product and this other one. Generally, what is the product over the primes of 1 minus p to the minus s? Using eigendecomposition, we were able to write down this product as Q, which is 1 over square root 2, 1, 1, 1, minus 1. Its inverse or its transpose. Then we have here a diagonal matrix. We need to evaluate products of this form. We make use of the Euler product formula for the Riemann zeta function. Suppose that S is greater than 1. S can be complex and we need the real part to be greater than 1, but here let's just focus on the real case. Zeta of S, which is summation k from 1 to infinity 1 over k to the s, is given by this product over the primes of 1 minus p to the minus s all to the minus 1. This result means that this product here is 1 over zeta of alpha. That product is 1 over zeta of 2 alpha. For completeness, let's derive the Euler product formula. Define the partial sum zeta sub n of s. It's the sum all the way to big N. The Riemann zeta function, zeta of s, is the limit of zeta n of s as n tends to infinity. we take for granted the fundamental theorem of arithmetic. Every positive integer can be uniquely written as prime p1 to the m1, prime p2 to the m2, all the way to pk to the mk. We can think of the primes arranged in an ascending order. Those primes are distinct. The m's are the powers of the primes. Suppose that the primes that we use and the powers are less than or equal to n. The claim is that this product here, in which every prime is less than or equal to big N, and then we have this bracket 1 plus p to the minus s plus p to the minus 2s all the way to p minus ns, this product of sums is greater than or equal to zeta n of s. This product of sums will give us each term in zeta n of s and also extra terms. Hence the inequality in this direction. For example, suppose that n is equal to 5. This product is the product of three brackets, 1 plus 2 to the minus s plus 2 to the minus 2s, all the way to 2 to the minus 5s. We have a similar bracket in which 2 is replaced by 3. In the third bracket, we have 5. If we multiply those guys, we get 1 to the minus s. Here is 2 to the minus s. Here is 3 to the minus s. Here is 5 to the minus s. And here is 4 to the minus s. There are many other terms. If we restrict the highest power of p to the minus s to n, and if we use primes that are less than or equal to big N, then the product of sums is superior to zeta n of s. The finite sum itself, since we are adding positive terms, is upper bounded by the infinite sum. The infinite sum is a convergent geometric series. This is equal to 1 over 1 minus b to the minus s. Zeta n of s is less than or equal to the product of those factors where p is less than or equal to n. Now we can take the limit of both sides as big N tends to infinity. On the left-hand side, we get the zeta function of s, and it is a finite number since s is chosen to be strictly greater than 1. On the right-hand side, we get the product over the primes of 1 minus p to the minus s to the minus 1. To establish this equality here, we need an inequality in the other direction. We have this product of sums. Now the sum includes b to the minus s to the power m, where m is an integer greater than or equal to n. Now this product of sums, if we expand it like what we did here, we get a finite number of terms. What we get is less than or equal to zeta of s. Take the limit of both sides as big M and big N tends to infinity. On the right-hand side, we just have zeta of s. On the left-hand side, if we take the limit with respect to m, the sum becomes an infinite geometric series equal to the reciprocal of 1 minus p to the minus s. When we take the limit as n tends to infinity, we cover all the primes. Using our inequalities 1 and 2, we get Euler's result. We are done. This product, because we don't have minus 1 here, is 1 over zeta of alpha. This ratio is zeta of alpha divided by zeta of 2 alpha. The final result is this diagonal matrix surrounded by Q and the inverse of Q. Multiplying our three matrices, we get this result here. We can write down this result in a nicer form if, for example, we know that alpha is a positive even integer. If alpha is equal to 2, we know that zeta of 2 is pi squared over 6. Zeta of 4 is pi to the power 4 over 90. We can put these here and get a simplified 2 by 2 matrix.